Hey guys, we are starting to talk about derivatives today. So today we're really just going to talk about the concept of a derivative and kind of what it means and the definition of it. We're going to talk about um, kind of some algebraic ways to find derivatives, including the power rule, and then how a graph of a function compares to the graph of its derivative. So I wanted to start today just by showing you guys the definition of the derivative. And so I've written it right here. We have two different notations that we use. One is the Leibniz notation, which is written like this. And this just kind of says change in y over change in x. That's what that dy and the dx means. And then this one you're probably a little bit more familiar of. The prime indicates it's the first derivative. Let's call this f prime of x of the function f of x. And so all we're doing is we're using what's called the difference quotient. This little piece right here that I'm highlighting is your difference quotient. And if we take h arbitrarily small, if we make it go to 0, which is what we're doing here with this limit, then this is just going to give us the instantaneous rate of change, which is our derivative, at this point x. So one other way that we can do it, if this gives us the function, so it gives us a function that represents all um, instantaneous rates of change. If we want to find the instantaneous rate of change at a single point, we can use the same formula, like I've written down here, except instead say we want to find it at 2 or 3, and then we would just plug in a for x and simplify it that way. So let's look at an example. So we want to use the definition of the derivative to calculate f prime of 3 given that we have our f of x is x squared minus 4. All right, so we want to use this definition of the derivative. We want to find f prime of 3. So we can use the same formula that I gave you up there. We want the limit as h goes to 0, f of 3 plus h minus f of 3 all over h. And now we want to plug in. We know what f of x is, and so we just want to plug in 3 plus h for every x in f of x. All right, so let's take a look. And we're going to have the limit as h goes to 0. Oops. F of x is x squared minus 4. So we're going to have x squared minus 4. Oh, golly. Let's see if I can get this right. I got this right. Sorry. We have x plus h all squared. This would be my x squared minus 4 minus, see, I just keep messing up on y'all. 3 plus h all squared minus 4 minus f of 3, and f of 3 is just going to be 3 squared minus 4, like this. And then we're going to divide the whole thing by h. Pull this down just a little bit. All right, so now we want to simplify what we have and see what we can cancel. So this 3 plus h all squared I need to FOIL. So this becomes 9 plus 6h plus h squared minus 4 minus 9. And then this will be minus minus, so that'll be plus 4 all over h. And then what should happen is all the constants should cancel, and everything that you have left should have an h in it. So let's see what we get. We have a negative 4 and a positive 4, positive 9 and a negative 9. So we got all those constants to cancel, and we end up with 6h plus h. And now, oh, sorry, just 6 plus h, because this h and that h will cancel, and then one of those will go away. So we're just left with 6 plus h. And we want to take the limit as h goes to 0, so this whole thing is just going to be 6. So what we've done here is we've used that definition of the derivative, and we've actually found f prime of 3 is equal to 6, and this is going to be the instantaneous, rate of change at x equals 6, or sorry, x equals 3. Or we could say it's going to be the slope of the tangent line at x equal 3. So now we can take the slope of the tangent line that we've calculated, which is 6, and we can actually write an equation of the tangent line for, we have the same function, x squared minus 4, at the same point, x equal 3. So I've actually done most of the work in the previous problem. I know that the slope of my tangent line, which I'm going to call m, is going to be 6. And now, in order to write an equation of a line, I need a slope and I need a point. Well, I know that at, say this is my function, and that's 3, and I want the slope of this tangent line. Well, I know that point is going to be on the line. So in order to write an equation of a line, I need a slope and a point. So I'm just going to use this point that is on the line that I'm finding the tangent line to. So this is going to be the point 3, f of 3. And so I just need to figure out what f of 3 is. So let's see, 3 squared is going to be 9 minus 4, so that's going to be the 0.35. This is the point I'm going to use. And then we have two kind of ways we can write the equation of a line. The one I like is the easiest one, and that's just your point slope form. And this is going to be y minus y1 is equal to m times x minus x1. And then I can just plug in x1, y1 is my point. So this is going to be y minus 5 is equal to, and then my slope was 6. So I'm going to plug in my slope, x minus x1, which is 3. And then if you wanted to write it in slope-intercept form, you would just distribute the 6, solve for y, and you would get y is equal to 6x minus 13. If I just ask you to write an equation of a line, this is perfectly acceptable. If you were, say, going to graph it, you might want to put it in slope-intercept form. Makes it a lot easier to graph. So it's pretty simple. So I showed you in the definition of the derivative that we can just write the derivative in terms of x. And this gives us, this gives us all the points, all the slopes of the tangent line at all values of x. So it kind of makes an equation or a function that will give us all of the slopes of all those tangent lines for our function f of x. It's pretty neat. So if we have a way that we can determine our function of our derivative without having to go through this whole long process of using the definition, then we can find these slopes a lot easier. So the one thing that we have that we start with is the power rule. So we have some x raised to a power. It doesn't matter what power. N can be a fraction, n can be a negative, anything can be a decimal, whatever. Then the derivative is just going to be, you take this power right here and you bring it down front. So that's why I have that in there. And then you subtract 1 from the exponent. So if we wanted to, really simple example, f of x is equal to x to the third, then my derivative, f prime of x, would just be 3x squared. So let's try one that's a little trickier. You have to remember that roots are also powers, and you want to rewrite those as in terms of their fractional exponents. And that rational expressions, single rational expressions like this one right here, are also just exponents, and you want to rewrite those using negative exponents. So you always want to rewrite so that it has the form x raised to the n power. So I'm going to take this right here, and I'm going to rewrite it. So the 5x will stay 5x. This becomes 32x to the 1 half plus x to the negative 4. And now I apply my power rule. So this doesn't have a power on it. Or sorry, you would assume the power to be 1. So we can think about the derivative of a linear function as always just being this number in front of x, or you could really apply the power rule. So I could bring the 1 down front, and that would become 5 times 1, x to the 1 minus 1. That just becomes x to the 0, so this is just going to be 5. All right, and now I'll write the 32 first. I'm going to bring down the power, so that's going to be 1 half x. I'm going to subtract 1 from this, so this is going to be 1 half minus 1. So down here I'm going to get 16x to the negative 1 half. So now I'm going to do x to the negative 4. So I bring this down, so that's going to be negative 4 times x to the negative 4 minus 1. So when you have negative exponents, they're actually going to become more negative as you subtract 1. So what's going to happen is this will now become, I'm just going to erase it so it's all in a nice pretty line, negative 4x to the negative 5th. And you could even simplify it a little more and rewrite it without negative exponents and without fractional exponents as 16 over the square root of x minus 4 over x to the 5th. I'm okay with your answer being the line above this one that I'm highlighting, but it's okay. Sometimes in multiple choice questions and so forth, you would want to change it. Okay, so now let's see if we can use this power rule, which makes everything nice and simple, to write an equation of a tangent line. This would be f prime of x. Let's fill in so everything's nice and complete. And so this is my f prime of x right there, my derivative as a function of x. All right, so now let's see if we can take this function, and we first want to find f prime of x because we want the slope of the tangent line at 2. So we need f prime of x. So I'm going to bring this down. 4x cubed minus 2. Derivative of a constant is just 0. So now we have our function, and we want to find f prime of 2. So this is 4 times 8 minus 2, which is going to be 30. So this is the slope of my tangent line. And now I want to write the equation just like we did before. So I have y minus y1 is equal to m times x minus x1. So this is going to be y minus, I need my y1. I always forget that. So I know that I want f of 2. This is going to be my y value. So this is going to be 2 to the 4th minus 2 times 2 plus 1, which is going to be, 13. Yep, 16 minus 4 plus 1. So that means that my y is 13, so it's going to be y minus 13 is equal to, the slope of my tangent line was 30 times x minus x1. x1 is just the x value, so it would be x minus 2. So you can simplify it if you want, and if you do, you end up with y is equal to 30x minus 47. Not so bad. Power rule makes it a lot easier to do that instead of trying to use the definition of the derivative, especially when you have something like x to the 4th. Oh. Okay, so now let's see if we can use the definition of the derivative to show that the derivative doesn't exist. So what happens if the derivative doesn't exist as a value? Then what's going to happen is the limit's not going to exist. Remember, the derivative is just a limit. So if we have the limit as h approaches 0 from the left, f of x plus h minus f of x all over h, this is not going to equal to the limit as x approaches h, as h approaches 0 from the right, f of x plus h minus f of x all over h. So if these two things aren't equal, then the derivative is not going to exist at this value h, this value x. So let's see if we can use the definition of the derivative to show that f prime of 0 doesn't exist for the absolute value of x. So if we look at it, a picture, absolute value looks like this. So if you look at the slope of the tangent lines as you approach 0, they're radically different slopes. So pictorially you can see that the slope of the tangent lines on this side are all going to be negative. Slope of the tangent lines on this side are all going to be positive. And at 0, there's no smooth point where they approach each other. It's just a sharp point. But let's see if we can show this algebraically. So we have f of, so we're going to look at the limit as h goes to 0 of f of x plus h minus f of x all over h. We want to look at this from the left, and we want to look at this when x is equal to 0. So this is going to be the limit as h goes to 0 of the absolute value of 0 plus h. I'm just plugging this in for x, and I'm substituting 0 for x. And now I'm going to have minus f of x, so that's just going to be minus the absolute value of 0 all over h. And what I end up with is, hold on just one second. Sorry about that. Okay, so this is where we were. We were looking at absolute value of x, definition of the derivative, and we're going to look at the derivative as h approaches 0 from the left side. So we plugged in x equals 0, we use our function, substitute it in, and what we end up with is the limit as h approaches 0 from the left side, absolute value of h over h. And this is going to be equal to negative 1, because as we come from the left, they're all going to be negative values. The top is always going to be positive, but this h on the bottom is going to be negative. They're going to be the same value. So when we divide them by each other, we're going to get 1, but since the top's going to be positive and the bottom's going to be negative, we end up with negative 1. So now let's see what happens if we come from the right. And we'll have the same thing. Absolute value of 0 plus h minus absolute value of 0 all over h. When we simplify that down, we get the limit as h goes to 0 from the right, absolute value of h all over h. Now we have the absolute value of h, which is always going to be positive, divided by positive h, because we're coming from the right, so all these values are going to be positive, so this is going to be positive 1. So since these two things are not equal, then the limit from the left and the limit from the right aren't equal to each other, and the limit doesn't exist. So this tells us, therefore, the f prime of 0 for f of x is equal to the absolute value of x does not exist. I think that's a pretty neat concept, and especially that we can show it algebraically. How neat is that? I love it when we can use algebra for things. It makes things so much more fun. All right, so now let's talk about the relationship between a derivative and its graph. So if we're just looking, our derivative shows the slope of all those tangent lines. If a function is increasing, then the derivative is positive. If a function is decreasing, then its derivative is negative. Or if a function has a max or a min, so say it looks like this, then all these kind of local maxes and local mins will all have tangent lines whose slope is 0, so the derivative there will be 0. So I have a little game that we're going to play where we're going to try to, this is a fun website, where we're going to try to match up a derivative with its graph. So what we have here is we have a puzzle, and these three are fixed. And so what we want to show is we want to see which derivative matches which graph. So I think that I'm going to start over here. And so I see that I have a function that's decreasing. until about I don't know, about negative 1.5. So that means that my graph is going to be less than 0 from negative infinity to negative 1/2 or negative 1.5. And then it's going to be, so this is going to be negative. It's going to be increasing from about negative 1.5 to positive 1/2. It's going to be increasing, so it means it's going to be positive, and then it's going to be negative from 1/2 to positive infinity. It's going to be negative because it's decreasing. So let's see if I can find one that does something like this. Let's see, this one is negative to 1, or positive to 1, and then negative. So that doesn't work. This one is negative to 1.5, negative 1.5, positive from negative 1.5 to 1/2, and then negative after that. So I think that's the winner right there. Erase all this. And we just want to go through, and once you kind of learn, if you think about the power rule and what's going to happen, you know the shapes of your graph, then you can see what's going to happen. So I'm going to put this one there. This one is going to be, it's increasing all the way up to negative 1 and decreasing from there. So let's see, this is positive to negative 1 and decreasing down there. So I hope that this helped. If you guys want to check out this website, I'll post it in the resource section on Edline, and you can play around. It's pretty fun. And I will see y'all later.